Okay, so thank you very much for the opportunity. It's a very nice conference, and I also thank the organizers to actually provide some financial support. Without that, it wouldn't have been possible to come here. So I'm going to talk about my understanding of what reduced order models should be, and how can we actually categorize them, and what are the plausible ways of actually extracting reduced order models from data. So, I mean, the content is very simple. So I'm just defining a very weak definition of a reduced order model. The only thing I want is some invariance. Then I will describe what four candidates could be for the reduced order models, and then I kind of eliminate three of them. And what remains are foliations, and then I'll talk about them in detail, and I will show some examples. So I'm coming from a mechanical engineering background, and what we really interested in is to speed up simulations of big finite element codes, because they can run for weeks and sometimes months, and we just don't want to do that. So folks, you can see this aeroplane fuselage, and they have all sorts of vibrations, many frequencies. What we are really interested in is the vibrations that can cause damage, that can break the structure, cause maintenance problems, and so on. So that's why I'm interested in reduced order models. So what I assume is a quite general assumption is that we have data, we have initial conditions, and the result of a time-bound map yk. So xk is what is going in, yk is what is coming out of this map, which is a time-bound map plus some noise with zero mean. And the question is that, okay, so how to find a low-dimensional description of this data if this n is actually large, right? Or you can call it, try to find an obstruction in the data, right? So they extract features that you are actually interested in, or capture an invariance. They are pretty much the same thing. Okay, so what I do want and what I don't want to do is here on this slide. So in many cases, data lies on manifolds, sometimes invariant manifolds, and some people capture the whole invariant manifold and all the dynamics on it and call it reduced order model. This is not what I want to call a reduced order model. What I want to call a reduced order model is if you have a cloud of data in a high dimensional space, and it can be on a manifold, but a high dimensional manifold, and I want to reduce the dimensions of it to, let's say, here, this is a two-dimensional data. I want to reduce it to something one-dimensional. So we have to find some order in the data. And in order to do that, you have to have a connection between the data and the model. So this will be mostly a function, right? And the connection can be, and also we might want some nice things, that the model is unique, it describes the data, that all the things that models can do, like predict the future, explains the phenomenon that you are seeing, informs your experimental design later on, and all that stuff. So there are two kinds of connections, right? You can either connect from the data to the reduced order model. So here's your data, and then you can create a function that maps onto something lower dimensional, and you can understand this as more like observables in Koopman theory, right? And obviously, if you're mapping from a higher dimension to a lower dimension, then there might be many different points in the higher dimensional space that map to the lower dimensional space, right? So, and in that case, basically, you're extracting a feature, right? So basically, one point on a lower dimensional space is some sort of a feature. You can do it the other way, and I call this an encoder, right? It's just from the computer science literature. But you can also call it a manifold submersion if you require this to have a Jacobian with full rank. All right, so you can do the other way around. You can map from the low dimensional space to the high dimensional space, and this is what I call a decoder. And here, basically, your map from the feature space creates a typical example of that feature in the higher dimensional space. And most of the time, you want this to be on an invariant manifold. Okay. So what can we do with these two types of connections? We can actually put them into so-called commutative diagrams. Some of them won't commute, others will. So if we have an encoder from both from the initial conditions and the result of the time one map, so after you applied f, then I call this an invariant foliation. And going through the arrows, right, through f and u, you compose them, and u and s, where s is the low dimensional map, you compose them, then you must have an equality in this boxed z, which is the low dimensional space. So this is the invariance equation here, and you basically want to solve for s and u, which are the low dimensional map and your encoder. And then you can see that f of x appears here. So that means that you can actually replace x with xk, the data, f of x with yk, and then you can fit this to the data. So this can be fitted to the data. And examples of this is basically Koopman eigenmodes, right? In that case, a special case, u is an observable, s is a linear map, and that's one of those. And Tony Roberts did some work on this before in the 90s, so nothing is really new. So the second case is the invariant manifold, where you basically use a decoder to map from the low dimensional space to the high dimensional space, go through the arrows again, find an invariance equation, but this cannot be fitted to data because the domain of the invariance equation is on the low dimensional space and you have no data on there, right? Without actually making some projections, which would be actually using an encoder, right? So that is not data oriented. So you can do autoencoders where you use an encoder and a decoder, try to write down the invariance equation as you go through the arrows, right? That's here. And basically you find that there's an f of x somewhere, you can replace it with the data, so you can fit this to data. This is not a commutative diagram, because you might notice that W maps to a lower dimensional space while F maps to a higher dimensional space. Very difficult to match them, right? You can do the other way around. You replace the order of the decoder and the encoder, and then you get a reverse autoencoder, for which you also get an invariance equation. So obviously there are lots of examples for invariant manifolds. Many people are doing it, mostly for when you have an equation. Autoencoders, again, many people are doing it. I don't need to say examples, but a reverse autoencoder can be actually quite curious. And actually, this is the case of Yanis's equation-free method. So basically, if you assume that f after some time collapses everything to a manifold, and to the manifold that you are actually interested in, then this diagram will approximately make sense. It's still not commutative, and doesn't commute, but still, yeah. All right. So, what do I mean by reduced order model? Well, basically, I mean invariance. So basically, in case of an encoder, if you have a trajectory in your data and you encode it, then that encoded trajectory must be the trajectory of a lower dimensional map. That's all it is. And if you have a decoder map pair, then it's the other way around. You create a trajectory with your lower dimensional map, and you map it to the space, and that must be the trajectory of the high dimensional map. So that's all it is, right? You have to have a connection that follows through trajectories. And so basically, now we can talk about the geometry of what's going on in invariant foliations, invariant manifolds, and autoencoders. So for an invariant foliation, when you have an encoder, the level surfaces, the collection of the level surfaces of the encoder create a foliation. I think many people know this already. So, and what invariance then means? So these are the leaves of the foliations, these curves, and the invariance means that the map of F, the high dimensional map, maps one leaf to another leaf, such that the parameter of the leaf is mapped forward with your low dimensional map. That's all. This is just a geometric point of view, and this is the invariance equation, which is exactly the same. Obviously, for invariant manifolds, you just have when you start from the invariant manifold with an initial condition, everything stays on the invariant manifold. That's all it is. Okay, so let's go to the autoencoder, and this is a slightly more complicated thing. So the conclusion is that it works, but only works if all your data is on an invariant manifold. So you have basically created a W function, which is a decoder, and it has an image, right? So this manifold M is the image of the decoder, and the invariance equation then says that from the pre-image of this manifold, F maps points to the image, right? That's obvious. But this must be the same as your encoder mapping to a parameter space, mapping forward with the low dimensional map, and mapping up with the decoder to the image. So this is for sure, right? This is surely happens. So these purple arrows, but you cannot really guarantee that this n, the pre-image of the function, is the same as the image, because that would be actually when you have invariance, right? When F maps the manifold M into itself, right? And then it would make things things make sense. So to ensure that this works, you want to make sure that the composition of this W and U, the decoder and the encoder, is basically identity on your data. But if you have a much higher dimensional data, then your model should be, this will never be zero, right? So this can never be approximately zero on your data. So conclusion, all that data must be on a manifold. Hence, in my definition, it is not a reduced order model, right? So in summary, what did we find out? We found out that, okay, so there are 4 cases: invariant manifolds, foliations, autoencoders, and reverse autoencoders. And what creates these reduced order model is the invariant manifold or invariant foliation. What can be fitted to data is the invariant foliation in the autoencoder, and the reverse autoencoder cannot do either of those, right? So, and that means that actually invariant foliation is a reasonable candidate here, and probably that's what we should use, or that's what I will use. Anyway, so there are special cases for invariant foliations. For example, when you have an equilibrium and when you want to find a foliation about an equilibrium, so or a steady state in this case, or a periodic orbit if you have a map, right? Period 1 orbit. And around the equilibrium, you have a Jacobian of your function. It has eigenvalues and invariant subspaces. So basically, you can select the foliation corresponding to a specific invariant subspace. In fact, it's the left invariant subspace because it's more like an adjoint type of thing, a foliation. Right, so we can define a so-called spectral quotient that is just some ratio between the logarithms of the eigenvalues about the equilibrium. And we consider the mu1 and mu to the new eigenvalues for which we want to create the foliation, right? And calculate this spectral quotient, which will determine and in which function class we will have a unique foliation. So this will tell you that how many times does it need to be differentiable? So the function that defines the encoder that defines your foliation. And in addition to that, for the existence, you must have some non-resonance conditions. And if you don't exclude internal resonances among your selected eigenvalues, then you definitely must use a nonlinear map, S. If you exclude internal resonances, then you can actually create a Koopman eigenmode or Koopman, yes, a Koopman eigenmode are calculated. Unfortunately, in most mechanical systems, those resonances exist, and well, that's why Koopman modes are not quite right for those things, and I will show you an example why. All right, so what happens if we already have a foliation? We figured out the dynamics, but obviously we actually want to pinpoint where this dynamics occurs in the space. Foliation only gives us on which leaves the dynamics occur. So the leaves are manifolds themselves, how manifolds are mapped onto each other, and that's really not precise enough for myself or colleagues in mechanics. In that case, we wanna for each leaf, we wanna create a typical example, right? A typical example where the trajectory will go. And we need to find an invariant manifold that is transversal to a foliation and complementary, so that the foliation and the manifold create some sort of a coordinate system in the full space, right? And for that, because we already have on encoder this U, we can actually create a very nice locally defined foliation about a manifold. So that means that about the manifold, the foliation varies linearly, so that's this U perpendicular. In fact, I can impose that this is an orthogonal matrix, and along the manifold, we already have a parametrization, because that's going to be the same parametrization as of the foliation. So I can use this encoder into a low-dimensional function and create a different encoder, which is obviously higher dimensional than what we have. And since we are only in the neighborhood of the invariant manifold, we can assume that the dynamics is roughly linear about that neighborhood. So the S map reduces to a B matrix, and we need to solve this. So in this case, we can find invariant manifolds as well as one leaf, the zero level set of a foliation, right? Right. Okay, so let's just try it on a 2D example where we actually know where things are. So this is just a linear map, non-linearly transformed with this V of x, and obviously we can, from this V of x, we can figure out what the foliation and the invariant manifolds should be, just calculating certain level sets. Okay, so then the actual invariant manifold that I have is this blue dashed line, and if we feed this data into an autoencoder, then the autoencoder exactly finds where the data is the densest, right? But it doesn't actually find the invariant manifold. In fact, I assume that the function representation, so that it always goes through the equilibrium or the steady state, so that's why it actually goes through the steady state. I can find invariant foliations quite accurately in both directions, so in the horizontal and the vertical direction, and I can also find this locally defined foliation about this invariant manifold here. So these look reasonable to me. All right, so what if we want to do it in high dimensions? And I must say that in mechanics we want nearly machine precision. So I tried deep neural networks for this, and I found it hopeless. So obviously there are guarantees, theoretical guarantees, that you can achieve pretty much any accuracy that you like, but when you start training them using the standard techniques, no matter whether you choose recurrent networks or other type of neural networks, they just won't converge. Anyway, well, not to the accuracy that I actually like. So in order to do that, I use a polynomial representation, which has coefficients, tensor coefficients. Obviously, when you have a high dimensional space and then you try to write a polynomial on a high dimensional space, these tensor coefficients will be enormous, right? So there must be some way to compress these, and there is some space and way, and that's, for example, one case is the hierarchical Tucker tensors, which decomposes this into matrix products. Physicists use it as matrix product spaces, and some people use tensor train networks and all that stuff. But this is my particular choice. And with this, you can actually calculate your accuracy, because you can calculate singular values of your tensor definition and so on. So if you know that the singular value, the slowest one, is nearly vanishing, you are there. Okay. So I tried this on a 10-dimensional system, and the HT tensor has rank in each of the nodes and the leaves as well. If you want, there's a preprint about this whole talk on archive. And the idea is to figure out from this huge system, which, I mean, it's a system of decoupled oscillators initially and scrambled up using a nonlinear transformation. Okay, so just to make it a bit more complicated. And the idea is to figure out the lowest vibration mode of this system and how the frequency along that vibration mode changes with amplitude, and how the damping ratio changes. In fact, these two graphs represent the exact reduced order model, because you can parameterize it as if you had a decaying vibration in a polar coordinate system. This would just be the instantaneous angular frequency, and this would be just about the radius, how it decays, right? So this is actually fully specifying the reduced order model. And I had 4 data sets, including very high amplitudes, medium amplitudes, and low amplitude data, and this is what I got, and I got near perfect match. If I actually increase the tensor rank, it will be much better. Anyway, I also tried it on a jointed beam, and the data I got from experimental colleagues in Bristol very kindly showed this to me. So this is a quite challenging mechanical example, because we cannot really characterize friction using a mathematical model without huge uncertainties. So the only way to study friction is by experiments. So what they did is that they did impact hammers tests and recorded the trajectories, the signals, and using this Takens embedding or some more optimal version of it, I reconstructed the state space. In fact, I needed to reconstruct not just the 10-dimensional space that they were meant to look at, but 32 dimensions and so on. And I figured out what these frequency and damping ratios are. All right. And obviously their experimental data is quite, I mean, I wouldn't criticize their methodology, but probably could be done better. All right. So when you try it as if it was a Koopman mode that you are looking for, then basically you have to restrict this linear map, or so that S map, to being linear. Okay. And when you restrict it, then unfortunately not everything is hunky-dory, because you have very small damping. You will have near resonances, and that would that would just complicate things and reduce your accuracy. It's like introducing singularity without needing to. Actually, oh, brilliant, thank you. So when you introduce singularities, that actually was removed by introducing nonlinear terms in this S map. That's probably not a good idea. And this is why the Koopman mode, even if you correct for all the distortions in the mapping of this observable, still only calculates the average of the frequency and somehow the average of the damping. So it's not quite right. I mean, you know, as with everything, I try to make the best out of it, but all comparisons are unfair, apples and oranges and all that stuff. So with a pinch of salt. Right, next, so this is probably the same paper that Igor mentioned in Nature Communications, where some colleagues of us basically reinvented the autoencoder, called it SSM-Learn, and actually obtained brilliant results in their paper, and I'm quite astonished what they could do. But I tried it to actually see whether this method would work as a reduced order model, and it just doesn't. So what happens is that we have the exact, oh gosh, never mind. So these red curves, and those are the exact calculations. This is another mode, this blue one. So I was curious whether it actually captured the other mode, but no, it didn't. This dashed blue line just captures something arbitrary. And same in the damping, it highly overestimates the damping. So this is 10 to the minus 2, less than 10 to the minus 2. This is 1. Yeah, so it's not quite right. Okay. Next, conclusions. So what did we learn? Well, within my framework, I considered all the possible possibilities for reduced order model identification. And I found that only foliations can be fitted to the data and be invariant at the same time when you want my definition to hold. That is, the model is lower dimensional than your data, right? And Koopman operator and the Koopman eigenmode is a special case of a special foliation. And this SSM-learn is actually an autoencoder. And there are many, many things that learn just a manifold. And what I didn't talk about, and you might be able to ask me, is that I think it's best for these type of precision problems to use something rather rigorous. So it's good to use compressed tensors, and actually to do the optimization. These tensors yield to a very nice optimization algorithm called Gauss-Southwell, which is, I'm not sure whether you heard of coordinate descent, but it's kind of similar. So many thanks for the opportunity, and I'm welcoming your questions.